Okay, hello. I'd like to share this video with any student who's currently taking or is studying the concepts of multivariable calculus. I think this is a good addition or supplement to any sort of studies you might be doing in a Calculus 3 course or a multivariable calculus class. I would have taught this topic during my semester here at Rice University as a multivariable calculus instructor. But due to the abbreviated semester, my students won't have the opportunity to learn this stuff or to see what I'm about to discuss. And I think it's a really cool 10-minute idea. And I think every student who's studying multivariable calculus really has a right to see this, what I'm about to cover. I remember when I first saw this, it was one of the first times in math when I saw a proof and thought to myself, wow, that's really cool. That's a really creative way to come to a conclusion and to do a calculation. So that's what we're going to do. We're going to be doing an integral, and yeah, stick around. So I'm going to pause this. All right. So here I've written the problem that we'll be working on, and it's a question that you could easily ask a student taking single variable integral calculus. Sometimes this is called calculus 2, or maybe calculus BC if you're taking AP courses. But this is an easy enough integral to describe, and it's an improper integral. So it's an integral of one variable, x, and you want to accumulate the area underneath the curve from negative infinity to positive infinity. And I've drawn the shape of the graph right there. It's and this graph this function is used to help model Gaussian distributions, and it's a totally practical function. And even this integral is a very important thing to know the value of. So really this number, whatever it is, it's going to be the area underneath this curve. It's that red area that I've drawn for you. And if you were in a calculus 2 course, you might start trying some techniques. I mean, I don't know what you would try to do, but maybe your first gut instinct would be to do a u substitution. Well, that's not going to work if you want to use, negative x squared as a u, because you don't have an x anywhere to help cancel differential. So just to kind of hasten this discussion, you'd be stuck if you were just trying to use single variable techniques. At least I don't really know of any. But you can actually find the value of this integral, which I will call I. We're trying to find the value of this number I. It's that red area. You can actually do it by looking to a multivariable motivation. Okay, so instead of computing I, I'm going to write a formula for I squared. If I get a formula for I squared, I can find the original value of I just by taking the positive square root. And I'll have a positive number because, you're looking at positive area above that, that line x equals 0, y equals 0. So let me write down what I squared is. It's going to be, I'm going to write the thing twice, right? Squaring is just e to the negative x squared dx, and e to the negative x squared dx. And so I'm going to do something a bit radical. Really isn't that radical. I'm going to, okay, this is the same, rewrite the expression. I'm going to rewrite this expression. But remember, I'm going to change a variable over here in that right integral. I'm going to just change it to y. It's a dummy variable, so it's the same number. Okay. Now, if you notice, this quantity right here is this is just I. This is a constant with respect to the variable y. So I can kind of reverse factor out a quantity. I can factor this back in. So I'm going to factor these, what's in these set of parentheses, into the integrand in my second integral. This is valid because it's a constant, right? You wouldn't bat an eye if this were a 4 in the red parentheses. So I don't know what it is, but you can pull that I right on in, and so I'm going to get, in fact, to help you sort it out, this is my purple integral. I'll write that on the outside because we're factoring stuff back in. So negative infinity to positive infinity of that red set of parentheses, negative infinity to positive infinity, e to the negative x squared dx, okay, times the function e to the negative y squared, and that gets multiplied by a dy. I'm going to take this to this next page, and I'm just going to copy this. All right, copy. We'll move on. Okay. All right. So I can further manipulate this. So kind of in the same spirit, this function e to the negative y squared, from the perspective of that innermost integral, is a constant function. So I can also reverse factor and push it back in. Okay, so what this will give me is, I'm going to keep that purple integral on the outside. The colors will hopefully help you keep things straight. And what will I have? This is still dy, but I'll be doing an integral from negative infinity to positive infinity. And this e to the negative y squared will come into this innermost integrand. So I'll have e to the negative x squared times e to the negative y squared dx dy. And lo and behold, this actually is an iterated double integral. So I'll write it out. I mean, this is exactly what you're doing when you compute an iterated integral. All right, so this is really just negative infinity to positive infinity to positive infinity of e to the negative x squared minus y squared dx and dy. Okay, so if you think about it, this set of bounds right here, oops, I want to use the highlighter, this set of bounds, what's it describing? It's saying x is ranging from the far negative left and the far positive right, and the y is ranging from all the way down to all the way up. That's the full plane. That's the entire plane. Okay, this describes the entire xy plane. Okay, and you might be like, all right, have we made our lives any better? At this point, no, this integral looks much worse, to tell you the truth. But there's maybe the best indicator of what to do next is we can look at this function in the exponent. I'm seeing an x squared plus y squared. Okay, there are negatives in front of it, but just factor out a -1. I'm really seeing x squared plus y squared. And when you're doing multivariable calculus, when you see x squared plus y squared, in your head, I hope your gut jumps to saying, exchanging that for an r squared. So maybe this integral is better suited for polar. So we're going to try to rewrite in polar. Okay, so I'll save a little bit of space here. We're going to try to rewrite this in polar. And how are we going to define the xy plane in terms of polar coordinates? Well, what are my theta values going to range from? I'm including everything, right? I'm not missing any slivers. I'm starting from the positive x-axis. I'm swinging all the way around to include it all. I'm starting here. I'm doing a full rotation, all of these rays. That's what I mean by that. So my theta is going to run from 0 to 2 pi. And what is my r going to range between? For each for each angle I form, I want to start at the origin. I don't want to miss anything, and I want to range out to infinity. So r is going to go from 0 to infinity. And if I change my function, all right, well, if I call this f, then I see f is merely e to the negative r squared. And then this is my dA in Cartesian. And don't forget, dA is r dr d theta. So these three pieces give us everything we need to assemble the same integral, but written in polar coordinates. So I'm going to run to this next page. All right, so this, and don't forget, we're computing I squared. If you follow the trail back to the beginning, that initial thing we were writing was I squared. So we're getting a formula for I squared, and we're saying, all right, this is the double integral of f dA over the entire plane. And we're going to do this in polar. So we said that's going from 0 to 2 pi in my theta bounds. My r is going from 0 to infinity in r. And we're doing e to the negative r squared and dA. Now here's the magic. The area element has that r factor. And so when a u substitution wasn't possible before, it is possible now. Because you can see how the cancellation is going to work. This r is our saving grace. Okay, so I'm going to take care of that theta integral first. I just don't like writing it around so much. So, we've got this 2 pi. That comes from that theta integral. I'm just going to write 0 to infinity e to the negative r squared r dr. So sure, let's set r squared equals to u, and this will give us r dr is 1/2 du. And so this integral is now 2 pi times the integral from, well, I should change my bounds. If r is 0, then u is also 0. And if r is infinity, then u is the square root of infinity, which is still infinity. I'm being a little sloppy with these bounds. You can see I'm clearly not teaching a Calc 2 course where we would be much more precise with, throwing these infinities around. But once you pass, Math 102 or Calculus 2, you sort of graduated from writing that limit everywhere, but that's beside the point. So if I convert this integral, we're going to have e to the negative u times 1/2 du, giving us pi times negative e to the negative u, evaluated at infinity and 0. And this is pi times negative 0 minus negative 1, and this provides pi. So we found that I squared is equal to pi. Goodness. And then, so thus, we found I squared equals pi. So I is root pi. And this is a really quick and clever way to compute the integral of this function. Okay. All right, I hope you learned something. All right.